Today's combustion webinar will be given by Waruna Kulatilaka, a professor of mechanical engineering at the Texas A&M University, who's going to tell us about advances in ultra-short pulse diagnostics for non-intrusive high-speed multidimensional imaging of chemical species in reacting flow applications. Waruna has wide experience in this field and looking forward to the talk. So I'll turn it over to you in just a moment. I'll tell the audience if anybody has questions for the speaker, please just put them into the chat window at the bottom of the screen here, and I'll read them out at the end and try and get through as many as we can in the time allows. So with that, the floor is yours, and take it away.
Thank you, Isaac. Good morning, good afternoon, good evening from wherever you're joining, and thank you for coming for the combustion webinar today. And it's my great pleasure to talk about some of these advanced ultra-short pulse laser diagnostic work we had been engaged over the last number of years, and it's specifically useful for variety of combustion diagnostics and combustion imaging work. So I will go through some of the initial developments and then talk about some of the work, more recent work we had been doing over in the recent times. So again, trying to get my point right. Okay, again, my name is Waruna Kulatilaka, so I'm a professor here in mechanical engineering at Texas A&M University. So seen here in the background is an aerial view of our university. So this is in College Station, Texas. So some of you wondering where that might be. I think everyone knows the North America and United States and where the Texas is. So it's in the southern part of US. And if you zoom in a little bit, we have three largest cities in the country in here: Houston, Dallas, and Austin, San Antonio. So if you draw a triangle between the three, we are right in the middle. So nice location in the southern Texas. And well, as I said a little while ago, get a little warmer in the summers, but then we get quite nice weather in here during most of the year. So College Station is a small town, and that's where the Texas A&M University is. So here at Texas A&M and in optical diagnostics and imaging, so that's the kind of the work we do in our lab. So we, as the name says, we do a lot of things with optics and lasers and optical imaging for a variety of applications. A lot of them are combustion and propulsion related work. So specifically different types of tools we use for these diagnostics. So these measurements. So listing here are some of the recent work from several different projects we had been engaged over the years. So femtosecond laser-induced fluorescence, so femtosecond LIF in short, is a powerful way of imaging chemical species in combustion and reacting flow applications. So that would be the main topic of the discussion for today. And then, but we also work on a number of these other different diagnostic techniques for a variety of applications for engineering research. So those applications ranging from, as we all familiar, like engines, gas turbines, IC engines, rockets, propellants, energetics, hypersonic flows. But as combustion researchers, we do most of those things in controlled laboratory environments. So some laboratory flames for combustion research. So these are some different types of combustion, different types of flames we have in our lab. Laminar flames, turbulent flames, piloted liquid spray flames, and then these are more like, dust explosion, the process safety type of applications, some energetics. A lot of these things related to some of the pictures you'll see here on the screen for a range of practical applications. So what are we interested as researchers, or combustion diagnostic community, is measuring several types of parameters. So physical properties such as temperature, pressure, velocity, density, and then the location of three-dimensional information of a reacting flow field. And then chemical properties, mainly the important chemical species involved in reactions. And then also particles such as dust, soot, and some larger particles in some applications come into the picture. So we're interested in those as well. So today, again, I will focus mainly on the chemical properties and species imaging So we have a number of different facilities around in here at Texas A&M. We do some of this diagnostic development work. So looking at the fundamental laser matter interactions, laser physics, how we can utilize some new advances in these laser systems for coming up with new types of diagnostics, or measure things which were harder to measure using traditional diagnostics, and then take them into applications. And we have some test cells and some fairly large scale facilities, and then also collaborate with a number of other researchers here on campus doing various other types of combustion and propulsion related research. So that's where some of these other systems down in here comes into the picture. So we can put our lasers. Sometimes they bring in their hardware into our lab, and sometimes we put our lasers on mobile cards and platforms and things like that, and then go into different hardware. There are different systems. So as I said at the beginning, the topic today would be new advances in ultra-short pulse laser diagnostics for combustion, of course. So when we say ultra-short pulse, what I mean here is mainly femtosecond duration pulses. So femtosecond is 1 femtosecond, as you see, like millimicro nano pico femto, so 10 to the minus 15th of a second. So very, very short duration laser pulses, which can bring in some a set of advantages for reacting flow imaging. So specifically, I will start with some background how this femtosecond laser-induced fluorescence, or LIF in short, where we had started some of this work, even going back into the days when I was at the combustion research facility at Sandia National Labs. We started going from traditional nanosecond lasers into picosecond lasers. And then later on, when I was at Air Force Research Lab, we started taking that into the femtosecond time regime. And then over the years, we had done a number of different developments. Specifically, since the title says in here new advances, so in the topic 2, 3, and 4, I will focus more on the more recent work done at Texas A&M, specifically high pressure hydrogen atom imaging in high pressure flames, and then using these femtosecond lasers or femtosecond pulses for imaging molecular species. Specifically, I will outline 2 examples of imaging carbon monoxide and hydroxyl radicals, CO and OH, in flame conditions. And then even most recently, we can take this advantage, take these lasers, the broad bandwidth of these lasers, which I will talk a little as we go on, and taking the advantages of those lasers to measure simultaneously multiple species. So for example, we have measured 2 species or 3 species at the same time using a single laser source. So this becomes a significant advantage when we go into chemical analysis of combustion systems, for example. So let me start with some background. This is again work starting about last 10, maybe more like 15 years or so, and then we will go into the next step, more recent work. So as combustion researchers or propulsion researchers, we are always interested in chemical environments, various types of chemical environments, and then these fundamental building blocks, atoms, particularly hydrogen, oxygen, nitrogen, and carbon. So those are the 4 atoms we encounter in most of these applications in the hydrocarbon combustion or plasma systems, looking at making better and a more efficient combustion system, and then reducing the pollutant formation like nitric oxide and carbon monoxide and soot from these flames. So it says there's always an interest of measuring these species, and not simply measuring, some is imaging. So do the 2-dimensional or even 3-dimensional diagnosis, so we can see where these species being formed, where these species being consumed, and then at what rate and what location in a particular reacting flow environment. So starting with atoms, so carbon, oxygen, nitrogen, hydrogen. So typically, when we want to use a laser to detect these atoms, here's an example of hydrogen atom, the simplest system, of course, you can get. If you look at the energy level of ground state, the first excited state or first few electronic states, this energy level gap in here lies in the vacuum ultraviolet region. What that means is, if you want to use a laser to excite from ground state to an excited state and look at the fluorescence signal, you have to use a VUV or vacuum ultraviolet laser. So what it says, vacuum ultraviolet means these lasers propagate only in vacuum, which is not very helpful for our practical applications when we do combustion, right? So we cannot operate in vacuum. When we have air and nitrogen and oxygen, N2 and O2, these lasers get absorbed. So that's when people have realized for a long time ago, when as early as some of these laser tools were available, one way of overcoming is using two-photon excitation. What it means by two-photon is we make the energy half, and then when you make the energy half, the wavelength becomes double. So by simple relationship of electromagnetics. So now instead of using a vacuum VUV laser, you use a UV laser. So and then it becomes a two-step excitation, which we call two-photon excitation. So two-photon excitation, in this case, this is for hydrogen atom. The excitation wavelength is 205 nanometers. So we can use two photons to go through this non-resonance intermediate step. And then you can look at the fluorescence emission, in this case, like H-alpha line at bright 656 nanometers as our signal. So it's simple, relatively simple to explain that way, but you can also use the same technique for use other atoms, and you just tune to the particular energy level of the different atoms. So if you want to do oxygen atom, you go to 226. If you do nitrogen, you go to 207. And then sometimes you can use some of these other species which are inert gases, which may not sound too exciting for reactions, but they do sometimes, because you can use this as seeders or tracer molecules, looking at the velocities and looking at the flow field mixing of reacting flows. And then you can extend the same type of two photon for some molecules like CO. But when you try to do this in reality, things get a little bit more complicated, of course, because always there's no easy way of getting everything at the same time. So when you do two-photon excitation, you can have a third absorption of a third photon at the same energy, and then you can ionize the atom. So you can have the fluorescence. So that is the signal we want. But in addition to the fluorescence, you can this, because of if you do have very efficient excitation, you can have population inversion between these states, and then you can have what you call stimulated emission, or in other words, a laser-like signal coming out, which is not the fluorescence signal we want. And then, like in any practical combustion systems, this is not only the H atom we have lots of other species, molecular and atomic species, like heavy species which are colliding. And then you have the decay of the excited state population through this collision or quenching, which is very hard to quantify in some combustion, in most complex combustion applications. So you need to keep all of these things in mind when you try to use this excitation scheme. So what we have done a long time ago, or about 10 or 12 years ago, most of these excitation schemes were done using nanosecond lasers. So an Nd:YAG nanosecond laser has been the workhorse laser for combustion diagnostics for many years, and even it is for most places right now, most part. So when you use this high intensity laser for this two-photon excitation, this is an indication. This is an example. You're sending in this laser through a simple Bunsen flame, and then you're looking at the H atom profile, H atom LIF profile, using a nanosecond laser. So what is shown here is a peak normalized signal of the profile of that H atom signal through the flame, because you see the peak at the flame front, and then there's no H atoms here in the premix zone in the middle, cooler premix zone, so there's no signal in the middle. And then you see the peak at the flame front, and then slow decay as you go radially outwards in the flame. So what is shown in here is once you increase your laser fluence, this signal gets the shape of this profile changes. So this is some indication your laser is actually perturbing the medium, doing something to the medium. So what is happening in here is this high intensity nanosecond laser or high energy nanosecond laser is dissociating some of the other flame radicals and creating extra hydrogen atoms, especially in this reactant, the product part of the flame. So one thing we did back at the Sandia National Labs in the early days was going from nanosecond into a picosecond laser. So instead of about 8 nanosecond or 10 or 8 nanosecond pulses, now we go about 100 picosecond pulses. You see this, I'm showing only one half of that radial profiles. You see that photolytic production gets reduced, but not completely. And then after a few more years, we started going into even shorter pulse lasers. This is some work done at the Air Force Research Lab when I was a research scientist there. In the femtosecond lasers, as you keep increasing the fluence of this laser, all you see here is just the signal to noise ratio get better and better, but the profile shape changes, remains exactly the same. So this is a good indication that photolytic interferences can be significantly neglected or reduced using femtosecond lasers. One of the advantages. And then comparing the nanosecond and femtosecond lasers a little bit, if you go into just a tiny introduction of the laser physics. So nanosecond lasers have this very short nanosecond pulses, but very short spectral bandwidth. So that these pulses are very short in spectrum. Whereas the femtosecond lasers with you can because of these mod lock oscillators and then amplifiers, the way the lasers operate, you get like very high bandwidth. So the band you get about several hundred or tens or sometimes even hundreds of nanometers bandwidth. So these lasers are inherently broad in spectrum, although they are very short in time. So you can sometimes go through, you can look in the frequency domain and the time domain. The frequency domain is broader, and then time domain is very narrow and very high peak intensity. So sometimes, so this is governed by the very fundamental basic principle of Heisenberg uncertainty. So shorter the pulse gets, broader the bandwidth. So just keep that in mind as we go forward, because how we manipulate this bandwidth, how we can take, sometimes we can take that into your advantage. So that's something I'll talk about. So these broadband femtosecond pulses, especially because they are very high intense, they are advantageous for this multi-photon or two-photon excitation, because the excitation happens or the signal scales by the square of your laser pulse. So when you do two-photon excitation, because you have high intensity, signal scales by square of that one. So shorter the pulse, you are more advantageous. So high peak power multi-photon excitation. And then the bandwidth effects I will talk more about as we go forward. So reduce photolytic interferences, as I showed in those previous examples, because of the high peak power, but the total energy is significantly lower. So you reduce these photolytic interferences, as we show in the previous example. These lasers operate at kHz-rate, so you can do kHz-rate imaging. And then because of the short pulse excitation, you can do some time resolved imaging, and sometimes even you can think about doing applying method for quenching correction, so quenching free measurements. So this work there has been a significant amount of work in the community of CAS. CAS stands for coherent anti-stroke Raman spectroscopy. So people use this short, the early 2000s, people started using different research groups using these femtosecond lasers for CAS excitation. So the only difference in here is you excite in the rotational or vibrational transitions, whereas in two-photon electronic atoms and molecules, we typically excite the electronic transitions. So we had been involved in this one, but today less, and myself and a number of other research groups had been involved with femtosecond CAS, but today let's focus on femtosecond LIF. So over those years, since those initial developments, we have and then other research groups as well extended these two-photon excitation schemes into a number of different species. So hydrogen atom is the one we showed before, and then you can do the similarly, as I mentioned, oxygen atom, nitrogen atom, krypton and xenon, for example, and a number of different applications for different extended research. You can looking at for some fundamental species transport, some plasma reactions, and then turbulent combustion, mixing studies, and then also more recently doing these two species simultaneously. So so that is a little background and some previous work leading into this research area. And then, as I mentioned, so when I say new advances, so I'll try to focus on three more areas in the recent years. Specifically, the work from Texas A&M, where we had been conducting, is taking these atom measurements first into high pressure. As combustion researchers, we are always interested in going to high pressure because that's where the realistic combustion systems operate at. So try to make these measurements into high pressure. So I will show some examples, and then discuss some challenges. And then specifically in this particular case, we have taken it from 1 bar, which is normal measurements, to up to 10 bar. So, and then we are in the process of trying to increase it even further into more realistic conditions. But I think as far as we know, that's probably the first time anyone has measured the atoms at any elevated pressure environments. And then extending, going away from atoms a little bit, but mentioned CO and to OH, two of the most interesting molecules, relevant molecules for combustion research, how we can use these femtosecond schemes for doing CO and OH imaging. And then, as I mentioned before, we can take the advantage of that extra bandwidth provided by femtosecond lasers, and then try to excite multiple species at the same time. So you have to be careful how to excite and detect. So that's on the simultaneous species detection. So let's start with high pressure shutdown. So a typical experimental arrangement looks something similar to this one. We start with the titanium sapphire amplified femtosecond laser operating at about 1 kHz. Typically, you can get about 1 or 10 kHz in these systems. Pulse width in the range of 35 to 100 femtoseconds. So ours is about 80 femtoseconds. So the output comes at 800 or 820 in that nanometer region. So we can generate the 205 nanometers for short-term detection using several different schemes. So in commercial systems, these are done using commercial optical parametric amplifiers, so called OPAs. The disadvantage there is the conversion efficiency is very low. So for doing gas-phase spectroscopy, we always need more laser power, less energy. So we have developed a home-built system. We have optimized this system for over the years, and which we call the femtosecond harmonic generation. Because if you take this laser to 820 nanometers, and then because 820 you frequency double it, then you get 420 nanometers, and then you double it again, then you get 205 nanometers. So that is what we needed for H-shutter. So by doing this one, you can get significantly higher conversion efficiency, although it's 2.5 still a lower number, but it's significantly higher compared to some of the commercial, what you can get from commercial systems. You send that beam through our combustion medium, whatever the flame we want to study. In this particular case, that's where our high pressure burner sits in, and then you can use these intensified cameras and intensifiers and camera systems for doing imaging of the fluorescence signal. So here's some schematic how when this FHE or fourth harmonic generation system works. You can see this blue color from 420 nanometers, and then the UV color comes out from this side of the system, and then we send it through this particular premix burner with a stabilizing this, so we can have a high pressure flame, high pressure flat flame. With a core flow around that one, so some parameters in given. So we typically operate this one with methane air for the results I'm going to discuss right now. So one of the major challenges using high pressure diagnostics is going through the windows of a gas cell or the combustor or whatever the facility you're trying to probe, because these thick optical windows can significantly affect the laser energy, and this becomes even more challenging when the pulses become shorter. So one of the first things we did we had to do was characterizing these transmission losses going through an optical window. So this is the typical optical window, about 1/4 inch thick in our pressure vessel or high pressure burner. So one thing you see in here is you increase the laser energy from low value to high value, but the laser transmitted through into the burner is actually going down as you increase your laser power. So there are some nonlinear effects and absorption losses happening through the typical window material, like fused silica, but you have to be very careful selecting the window material, like in this particular case quartz is more helpful. And then also some focusing lenses and other transmittive optics you use in your optical train to analyze the transmission losses, because the idea is to maximize the transmission and then also minimize the distortion of the characteristics of your laser pulse. So once it's all been said and done, we can start taking some images like this one. So this is an excitation scan. Now again, keep in mind, as I mentioned before, that the line is significantly broader compared to nanosecond laser. So you see this several nanometers wide excitation scan at around 205 nanometers for H-atom. So you scan your laser, so the broadband laser over the excitation transition, and you get an excitation spectrum. So just to verify that we are looking at the right thing. So you can scan this wavelength, and then you can look at the excitation transition, and then also you need to verify that you get the expected quadratic dependence of the. So this is 2-photon excitation, so the signal scales as a square of your laser pulse energy. So you verify the quadratic dependence. Why this is important is because I mentioned about these other parasitic effects which can come like quadratic interferences and simulated emission. those can be identified or diagnosed if you see non-quadratic dependence. Sometimes when you have a lot of quadratic production, you get more higher than quadratic dependence. When you have a lot of stimulated emission, you get sub-quadratic dependence. So it's important to verify that for all these pressure conditions we're trying to investigate, we get a good quadratic dependence. Okay, so laser power dependence, we check that one as the very first thing, verify that up to the pressure range we operating at, and then good to go. So and then also, as I mentioned, stimulated emission, or in this particular case we stimulated emission, but along the beam probe region, when the stimulated emission signal comes in, it gets amplified. So you can amplify stimulated emission, or you basically get a laser beam, like a directional beam through your probe volume. So that is bad, because specifically in terms of when you try to quantify these signals, so we want to make sure that we have the stimulated emission, or if we don't have the stimulated emission, that's a good case. So in this particular case, we check the stimulated emission signal as a function of our laser energy. So we see when the laser energy reaches some value, threshold value, the stimulated emission signal starts, because of that population inversion happens very, very efficiently at those higher pulse energies. But one advantage, one unintended benefits, if you will, came from going through these optical windows is when you go through the optical window, you stretch your laser pulse in time. So that femtosecond, 100 femtosecond or 80 femtosecond laser pulse gets a little bit longer, to up to about 200 or 250 femtoseconds. Because of that one, that excitation efficiency gets a little bit lower, pulse gets a little short in time, and then the stimulated emission signal basically disappears in the pulse energies we investigated in here. So with the burner window on, which is shown by the red line, there is no directional stimulated emission signal, which is an advantage, because we don't want the stimulated emission signal. What we mainly want is all our excited state population going back down through fluorescence. So once we confirm that some of those initial characteristics, we measure these H-atom line profiles through different heights of the blade, different height at a specific height, and then also at different pressure conditions. So going from 2 bar to 5 bar to 10 bar. So these are typical line images, and you you integrate that image. You can see the radial profile of H-atom through those flames. This is a slightly rich flame, so you see this diffusion-like flamelets at the end. And then you see a nearly flat region here in the middle. And these measurements also mesh very well with 2D flame calculations using unicorn code with our collaborators. So we actually are about to present some of this work in the upcoming Combustion Symposium. And then, as the interest is in investigating the pressure effect. So this is how the signal varies when we go from 1 bar to 10 bar. So the number density increases linearly with the pressure, but the signal does not. Why? Because we have lots of other number of other effects happening. So the laser beam absorption and the quenching gets significantly stronger. So because of those things, the actual signal starting from 1 bar to 10 bar drops to about 20% compared to atmospheric conditions. So you can apply the quenching corrections. So quenching corrections will take the signal back. So because in this particular flame, we can model the flame, and then we can get the collision of the quenching partners, and then the temperature profile from the calculations. You can use that for quenching correction, but you still have significant signal still does not go linearly with the pressure because of signal absorption, laser beam trapping, and other things which needed to be taken into account, which is always a challenge in quantitative measurements in these kind of environments. So nevertheless, we have compared the relative H-atom signal with as a function of equivalence ratio in these flames. So these are again showing for a few different pressures: 1 bar, 2 bar, 5 bar, and 10 bar. So H-atom LIF signal as a function of the flame equivalence ratio. So going from lean to rich, and then also compare with the equilibrium H-atom number densities as predicted by the red line. So in the lean flames, in the or low pressure flames, and then also in the low pressure flames, we see some super equilibrium type of fs-atom concentrations in the higher equivalence ratios. In general, the profiles agree reasonably well in the up to about slightly rich flames. But when the pressure gets higher and higher, we get larger discrepancies in the low equivalence ratio or lean flame side. So which is not predicted very well using the equilibrium calculations. So I think that's where we think there might be some level of super equilibrium fs-atom concentrations, and then also we need to see whether we see any level of photolytic interferences, which we are investigating right now. But with this initial success, we were able to do some two-dimensional images. Again, the one thing need to keep in mind here is the fs-atoms are very low number densities, so 10 to the 13th, 10 to the 14th per cubic centimeter type of number densities compared to several percents of other molecular species. So the signals are very low, so you cannot do like a full 2D image in one shot. So what we do in this case is we take a line image and then we translate the burn up and down, and then we combine those line images, the 2D profile. So shown on the right hand side is for one half of the flame, the experimental 2D profiles, and then the left hand side is a calculated fs-atom mole fractions or fs-atom number density using the unicorn code. Qualitatively, we get reasonably good agreement with the shape and the location of fs-atom. So this is a good indication that this method can be useful for high pressure applications. Again, as combustion researchers, we are always interested in turbulent combustion. So turbulent combustion means the 2D or 3D flow field is varying in time. So it's always an interest of doing these measurements as snapshots, or which means single laser shot measurement. So we have investigated the possibility of doing these single shot measurements as line images. Again, doing some tricks for our detection channel, increase in the efficiency of the detection, and then also trying to get the maximum possible amount of laser into the probe region. So we have seen limited success with the. So this is the original measurements which was shown in the previous one. So the frame B and frame D shows with this improved camera setup using an EMCCD camera. The only limitation there is these cameras don't go at kHz-rate, so the measurement frequency gets a little lower. But nevertheless, we can increase the signal to noise ratio, and then as the method gets even more promising going into high pressure applications when you have EMCCD cameras coupled to these intensifiers. So with that in mind, or with that moving forward, let me quickly go through two of the molecular species. Now we extend in the same applications. In this case, CO and OH, carbon monoxide and OH. So again, as two of the most important radicals for combustion research. So carbon monoxide also, as I mentioned before, has this two-photon excitation. So the two-photon excitation from ground state to B state is at 230 nanometers. So you see 230 nanometers of two-photon excitation, and then you can look at the fluorescence from this angstrom band. Now keep in mind, because this is a molecule, now we have the rotation, row vibrational energy level structure. So you can from the angstrom band, or you can have the collisionally populated third positive band. So third positive band emits in the UV side, and then the angstrom bands emits in the visible range. So angstrom band B2A emission is a focus for this study, and which has been the primary method for CO detection in flames. So here's a laser system. In this case, now we go back to that commercial low PA, because we cannot get to 230 nanometers using the harmonic generation scheme, because that's outside the range of the tunability. So we go through a commercial scheme of start in this one and go to 230 nanometer, and then send it to the burner, and then looking at the spectrum. So one of the main challenges with CO detection is interference from C2, because CO typically present in rich flames, and then the rich flames you have unburned hydrocarbons, and then C2, and these strong C2 swan band emissions sometimes can overwhelm your spectrum. So interfere quite a bit with CO LIF signals. So the initial work on this one is trying to do the time gating. So you can limit your time gating, because the swan band emissions come from as flame emissions. So and then some of them are laser generated. So laser generated emissions can be corrected by or the flame emissions can be corrected by reducing your laser pulse. So this is going from 10 nanoseconds to 100 nanoseconds if you do 1000 nanoseconds. So basically the bottom line here is you should try to get your detection bandwidth as short as possible. So when it is all said and done, you can make some CO measurements in these flames. So again, these are atmospheric pressure flames, but you measure the CO profile as a function of equivalence ratio in this premixed methane flame. So you get a very good agreement with equilibrium calculated CO profiles as a function of equivalence ratio. Two types of flames. So this is a methane air flame, and this is an acetylene air flame with a lot of soot in this one, especially when you go into the rich side. You might see slight disagreement. Again, it's not quite clear whether the model is predicting exactly accurate, or whether we have some discrepancies, but within it's of the measurement between the experiment and the calculations in the high equivalence ratios, and it matches pretty well in the low equivalence ratios and the lean side, where we don't have much CO anyway. So have extended this into 2D imaging again. So you can do some limited 2D imaging, single shot 2D imaging like shown here, but sometimes you can do some of these average images, and then stack them together to get the full 2D CO profiles in these flames, which gives a nice indication where the CO is being formed in these flames. And then you can generate some line profiles out of those images, and you can we have extended that into some other flame conditions using liquid fuels. When you burn kerosene or jet fuel, well, starting with a simpler fuel, of course. So you get like significant amount of turbulence in this piloted liquid flame as liquid spray burner. So just to give a little background, so we have methane air pilot flame, and then we have in this particular burner we have a injector, or basically a nozzle creating a spray of atomizing liquid directly into the flow stream. So the pilot flame is holding as a stabilizer to have a steady state spray flame. So this gives nice test case again to look at the CO emission. So this is okay. Here's a picture of that pilot flame. We have that injector in the middle of the premix flat flame of the Mechana burner. And this is when it's operated at a few different flow rates of the liquid flame. This image doesn't show this. These are 2D CO images, short average 2D CO images, and then we also take the radial profile, so height above the burner along the center line, and then at few different equivalence ratios. So these things we have compared with some spray flame models, and get a reasonable agreement of these radial profiles, and then also as a function of height. So this is radial profiles at few different heights of the burner, and then a few different flow rates of the liquid jet. So again, CO as a function of radius, and then at different heights. So some agreements and some disagreements in some cases. So in our publication we discuss some reasons why in some situations why there might be disagreements. Okay, so extending this into our second molecule, which is hydroxyl, again one of the most interesting and seek after species in combustion. So in this particular case, we do single photon excitation. We call one photon excitation, because hydroxyl has these nice electronic transitions in the UV range. So in the 283 or 308 nanometers. So if we look at the excitation spectrum of hydrogen, we see this of OH hydroxyl. You have this large number of row vibrational transitions in this rotational transition, like Q1 file. One of these lines, for example, is what you typically excite using a nanosecond laser, because a laser has about the same line width as the excitation transition. But in the femtosecond laser, you have this significantly larger bandwidth. So you, instead of exciting this one line, you exciting this multiple large number of lines at the same time. So here are some of the results. Now, just jumping forward, that we can do this OH images in a turbulent flame, for example. But before I go too much in that, before I show the results from there, and then also from a high pressure application, one of the advantages in here is when you increase the pressure, these spectral lines broaden and they shift. So line broadening and shifting. So when you use a narrowband nanosecond laser, for example, this line broadening and shifting can be significant because the laser is typically narrower than the spectral transition. So when the laser is narrower than the spectral transmission, this line this line broadening and shifting has to be taken into account, or sometimes we call spectral overlap corrections, which becomes challenging, especially if your pressure is varying and if your turbulent conditions are varying. So this line broadening and shifting becomes an issue. So one thing we showed using one of our recent papers in this broadband second lasers. Now the femtosecond lasers, instead of 0.7 wave numbers, we have about 150 or sometimes even up to about 400 wave numbers. So this higher bandwidth excitation can be advantageous because now your laser is significantly broader than your spectral transition, so you don't have to account for this line broadening and shifting. So with that in mind, we look at the excitation spectrum, and then it matches reasonably, pretty well with the calculated excitation spectrum. And now we are after with that initial demonstration, we were ready to take this into our high pressure burner. So now we take the tight sapphire laser, and then again to going through those optical windows and doing this high pressure, we always want to have more laser energy. So we had a real limitation. What the way we overcame that was using another home built system, actually, well, a variation of the previous home built system, I would say, because you can tune your laser all the way up to about 850 nanometers and then generate the third harmonic. So the third harmonic, instead of going through the optical parametric conversion system, now you generate the direct third harmonic. Third harmonic comes at 283 nanometers. So that is what we needed for OH excitation. And then we put that through our high pressure burner. So this is the schematic of the high pressure burner. Yes, this is that. And the flame looks something similar to this one, slightly rich flame. And then before you do actual measurements, you want to make sure you characterize your laser dependence, make sure your signal scales linearly, in this case, single photon excitation. So make sure your laser power dependence is good. You don't have other additional interferences, which is good for the most part, but we typically don't go into these high laser energies, which we see some level of saturation at atmospheric pressure conditions, but at 10 bar and then higher pressures, you get signal becomes lower because of those absorption and other losses I mentioned, but you get nice linear dependence. So, so you want also, since we do the broadband excitation, you want to make sure you look at your emission spectrum and make sure what you're detecting is exactly what you want. In this particular case, emission from OH signal. So this is an excitation spectrum as I showed, but this is a corresponding emission spectrum. So you can match this corresponding emission spectrum and compare with the calculated LIF-based spectrum, for example, and easily verify that indeed all these transitions you see as well, they change the intensity, relative intensity change as a function of pressure, but these transitions what you see is indeed from OH emission lines. So you're ready to put a spectral filter and then collect all these transitions as your fluorescence signal, and so when it is said and done, it will look something like this. So you get this. These are some average images from between those flat flames and three different pressures and three different equivalence ratios. So when the flame gets rich, you have this. The most of the burning happens on the outer edge in the diffusion-like flame, and then when on the lean side you get fairly uniform reaction zone in this flat flame. So from these images, so from the line images, you can generate two radial profiles. So this is OH profile in a lean flame and OH profile in a rich flame as a function of radial location. You get this dip in the middle because you don't have the most of the reaction happens here in the outward radial locations. You get these huge peaks, corresponding huge peaks from there. So And then we compare this with some numerical calculations. Again, the unicorn code can do 2D calculations using this for these flames. And then, of course, since this is this fluorescence scheme, you need to account for the collisional quenching. In this particular flame, since you can calculate the multiple species, so you can use those multiple species to apply quenching corrections. And then most of these OH quenching cross sections are known, so you can apply known quenching cross sections and then try to quantify your signal. And this one right here, this is shown in the dotted line, is quenching corrected signal. The other main advantage of doing this one with getting the high signal to noise ratio and doing this at kilohertz, now you can do kHz-rate imaging. So this is an attempt to do single shot kHz-rate imaging of OH in this same high pressure burner. In this particular case, what we did was we just took out the stabilizing disk. So you get this very high buoyancy effects in the flame. You see this buoyancy flapping kind of thing, and then you can see the OH distribution. This is a 1 kHz movie. These are some still frames. You can see the different types of flame combustion events happening in this burner at these pressures. So get reasonably good signal to noise ratio at 10 bar. So this is a good way of measuring OH in the high pressure environments in this case. Okay, so with that in mind, I will switch to the last part of this one. So you'll see this the broadband at femtosecond pulses can be advantageous because you can try to excite multiple species at the same time using one laser. So indeed, we have tried to take the advantage of that one, and we have in this case, I will show two examples. One is doing H and OH, hydrogen atom and OH at the same time, and then this most recent one. This is we're doing NO, but we can detect the O atom and O2 also at the same time. So let's look at the NO and O and O2 system. I will leave the H and OH system out for today. So NO has excitation at 226. So most of us familiar with this wavelength when you're trying to detect NO. So 226, but at 226 you get you can do a 2-photon transition for O atom as well. So you can try to excite O and H at the same time because the absolute wavelengths are close enough. The femtosecond laser is broad enough, so you can do the 226 excitation single 226 single photon excitation. This is slight mistake in here. 226 single photon and then 226 2-photon excitation for O. And then when trying to detect NO, it's a common problem in most combustion applications because this hot O2, hot oxygen molecule, Schumann-Runge emission can overlap at the same wavelengths and then interfere with the O2 signal. So we will try to take that as an advantage. So if we try to be spectrally specific and you know exactly what you're detecting at what specific wavelength, you can try to detect all these three species at the same time. So typical experimental arrangement again looks something like this one. So we go to our Ti-SFI amplifier and optical parametric oscillator to generate 226. So this 226 has a broad enough bandwidth, so we can excite all these three species at the same time. So in this particular case, we put a small calibration burner, like typical Henken calibration burner with a flat flame, or a Bunsen type flame. So you can look at the spatial effects of the flame front or more uniform effect from this flame. So the first step looking at the excitation transitions. So you're looking at the excitation bandwidth. You scan your laser from 220 to 230 nanometers, and then you can mesh very well the LIF emissions excitation spectrum of NO, and then excitation spectrum of O2, and then hydrogen atom has a narrow transition, so this is broadened by the width of your laser. And then also you check your laser power dependence. So this is a laser signal. Three of the emission signals as three of the species LIF signals as a function of laser energy. NO and O2 is a single photon excitation, so nice linear dependence. And then O2, so O atom is 2-photon excitation, so you get this quadratic dependence. So that part is good. So once it's said and done, you go back and check on your emission side, because since you do this broadband excitation, you can excite multiple things at the same time. So if you need to carefully set your emission detection filters, so you detect the right species at the right emission wavelength. So NO, we focus on 236 nanometers in this range. About the detection parameters are listed in here, but at 236 nanometers, you get this relatively interference-free NO line. And then similarly, you can zoom in or go with high resolution grating, and detect that line, and then also confirm that with a simulated spectrum. You can confirm that is indeed the O2 line. Similarly, you identify from a 2D image. So this is when you try to detect in a Bunsen flame, you have this flame front. So in the middle there shouldn't be any oxygen atoms. So there's no oxygen atoms in the middle. Of course, you have oxygen O2 in the middle, but you don't get emission from O2 because it's O2 Schumann system is active only at higher temperatures. So you don't get any O2 signal here in the middle as well. But when you go up in the flame, you don't see, you have the fairly uniform region. So you see kind of like a Gaussian like distribution of these species. So this is a line image. So the wavelength on this side, and then the radial distance on the other side. So you're basically imaging onto the slit of your spectrometer. So you can identify these specific emission lines, and you can generate the spectrum, and then you can find out the regions where you can do separate interference-free detection of individual species without which we can quantify. So when it is all said and done, identify the detection regions as listed in here. What is shown in here is the three signals, LIF signals, NO, O, and O2 as a function of equivalence ratio, and then compare with the Cantera calculations. So in this one, you see the peak O-atom signal. That's a slightly stoichiometric or slightly rich flame, and then the O2 goes down. Of course, flame gets richer and richer. There's no excess oxygen, and then NO agrees very well on the lean side, but NO does not agree with the equilibrium calculations on the rich side. And then in this particular case, what is known in here, what we found out later on, we try to compare with the previous NO measurement using a nanosecond laser, which agrees reasonably well. And then this is an indication that you might get a lot of prompt NO, which is not predicted by the equilibrium calculations in this case. So this work will be also presented at the Combustion Symposium in a couple of months. All right, so in summary, I think I talked about some background leading into this femtosecond laser-induced fluorescence diagnostic development, specifically going from nanosecond to picosecond to femtosecond lasers, and then using in the more recent work, taking the advantage of the high intensity femtosecond pulses for H-atom imaging, for the taking this H-atom imaging into high pressure flames, so going up to 10 bar in this particular case. And then molecular species CO and OH, specifically I showed some single shot OH images at elevated pressures. You can use this one to look at flame dynamics and turbulent effects, for example, when you do 2D imaging. And then taking the advantage of this broadband pulses for simultaneous multiple species. So we have done up to 3 species so far, NO, O2, and O. All right. So with that, I would like to thank my group, number of students involved with this work in the present and past, specifically Yajun Wang, Ayush Jain, Pradeep Parajuli, and Matt Hay are the 4 PhD students who did most of the work with this femtosecond diagnostic work, and then other students from some other projects. So I'd like to thank them all and some of our funding agencies. And I will stop there.
Okay, great. Thanks. It's a very interesting talk. A lot of topics covered, and we have several questions from the audience. So I'll just take them in their order that they're received. First is actually from me. I think I interrupted your talk in the middle, so I apologize for that. On slide 18, why does the transmission efficiency through the windows decrease with increasing pulse energy? What's the mechanism responsible for that?
Yes. So very good. because these pulses, you don't see this effect typically with the nanosecond pulses, but because of the high intensity femtosecond pulses, you get some nonlinear effects in the window material. So you get pulse stretching and you get some harmonic generation. Sometimes if you try to send a lot of energy to one of these windows, you see like different colors coming out. So you see some frequency harmonic generation, higher harmonic generation happening in the window material. So all of this actually result in loss of the actual pulse, the actual wavelength you need.
So you're changing the wavelength of the laser, not damaging the materials that you're passing through. Is that?
Well, eventually you will damage the material too.
Okay.
Yes.
Great.
So typically we stop before that.
Yeah, hopefully. Okay, next question is from Todd Fonsler. I hope I'm pronouncing that correctly. On slide 22, are these single shot measurements or averaged over many shots? And if so, how many?
No, these are single shot.
Single shot. Okay.
Yes.
Great.
Yes. Yeah, we do. The one down shown in here, the one we use to create the 2D images are average because you don't get high enough signal noise ratio. But when you do like a nice enough fine line, you can do line imaging and you can get single shot.
Okay, actually, while we're on this slide, I'll just throw in one question that just occurs to me. On the lower picture here on the experimental versus the model, it looks like the signal levels are higher a little bit further downstream. Is that an artifact or is that real?
Well, yeah, we thought it was an artifact initially when we first look at this one, because we thought we get some kind of a scaling effect or some kind of non-uniformity in the burner, but seems like this is real. So so the model is not predicting this one. So again, the question is the model taking into account? Well, what you need to keep in mind. So you have the stabilizing disk right above here. So the squinch. So there is some kind of a heat transfer effect going on in here. You would think the experiment will show more quenching effect from the stabilizing disk, but in this particular case, it's predicting the other way. It's a little bit of an open question at the moment. We don't know.
Okay, great. Next question is on slide 26. You mentioned the EMCCD camera performs better than the, I believe it's an intensified CMOS camera. What's the advantage of one over the other?
No, well, both are intensified. So we actually, what we did was we used well, of course, if this question coming from you, you know exactly this two-stage intensifier. So we use a two-stage intensifier and then high-speed camera on the back of it. So CMOS camera. So that's what we typically do.
So they are both intensified. Okay, gotcha.
They're both intensified, but the CMOS camera has significantly higher higher noise, right? So what we did in that case is took off the CMOS camera and then put an EMCCD camera. So EMCCD camera will, the chip noise, the readout noise is significantly lower. You get like a much nicer signal to noise ratio. The disadvantage, of course, it doesn't go fast. Right, okay. 10 or 30 or 20 or 30 hertz maximum.
Okay, great. The next question's from Jay Gore. Could you please provide detailed references to the piloted liquid spray burner geometry, and in particular, how serious are the effects of the burner lip and heat transfer to it on the CO and OH concentrations? Yeah, absolutely.
If you're interested, actually, I can share the paper. We have a paper which we did the simulation and comparison. We have actually 2 papers on this one, I think, on this one. So we described all the flow parameters and the burner geometry. So what was the second part of the question again, Isaac?
In particular, how serious are the effects of the burner lip and heat transfer to it on the CO and OH concentrations?
Yeah, well, so we are looking at the liquid spray flame. So there's a significant amount of heat transfer on the pilot frame, but the liquid flame is essentially lifted. So liquid flame is not even touching the. It's not, well, it's touching the spray is touching, but the flame is not touching the tip. So I don't think the
liquid flame, if I may, can the liquid flame be run without the pilot?
No.
So the pilot is essential, but you feel the pilot is not interacting with the flame. It's essential for stabilizing the flame, but not necessarily affecting the radical species. Is that sort of the hypothesis?
It does maybe at the beginning, because it acts as like a flame holder, right? If you were, because it generates radical pools, so the flame can stabilize. So it'll affect the ignition and flame holding on the bottom part of the flame. But if you go up, like, I don't know whether you can see my cursor or not, but
yes, I can.
If you go up, like in this part, like we don't see any effect from this pilot, the stabilizing flame or the pilot flame basically stops right around in here. So it doesn't go up. So it generates the radical pool to stabilize the combustion, but it'll affect the combustion overall. But there's no species coming off directly from the stabilizing flame into the main flame in higher elevations, if you try to put it that way.
Thank you.
Great. And the final question from the audience, myself once more, is just sort of a big picture question. What would you say is the biggest challenge to doing the femtosecond LIF imaging at elevated pressure? You mentioned several different factors, but what would you say is the most challenging one? What needs to be addressed?
So it depends on what species you're looking at, to most part, right? So you see, like, because I said, like, a lot of challenges with H atom. For two reasons there. One is the wavelength is 205. So further down you go into UV, it becomes harder and harder. All those previous effects I mentioned about the nonlinear effects, signal absorption losses through the windows, and because you're getting closer to the vacuum ultraviolet. So that's one challenge with H. And then another challenge with H is or species like atoms is the number density, right? Number density is extremely low. So we get the advantage or that advantage, and then the third one is a two-photon excitation, because excitation, the two-photon cross sections are significantly weaker. So we get the opposite of that in all three of them when we go to this H atom, OH, because now from 205 you go to 283, so it's more the windows are more forgiving, if I put it that way. And then also the single photon excitations or the cross sections are higher, and then you get higher number densities. So it's always the balance between what you have and what you're looking for. But on the other hand, I think we were pretty pleased that we could do H atom measurements at 10 bar, because as far as we know, there's no H atom measurements in any elevated pressures in the reported in the literature.
Certainly is challenging, yes. Well, that covers all the questions from the audience. So I think it's time to close out the seminar. If anybody in the audience would like to just turn on their cameras and thank the speaker, there's a chance to do so now. And if not, we'll close it out. So